this is like the grand opening of our organic chemistry store. All right, so we are now going to start talking about reactions, and we're totally ready for this. So we're going to be talking about substitution reactions for the rest of our organic chemistry life. So we're going to start this out with some basic things that you already know, and hopefully this will sound familiar. So first of all, we're going to talk about substitution reactions. There's two kinds of substitution reactions that we're interested in, both of them very important: concerted and stepwise. So this conversation is mostly going to be about concerted mechanisms. We're going to talk about what it means to be concerted, what it means to be stepwise, and then we're going to talk primarily about concerted mechanism here, which is SN2. So the concerted mechanism involves the breaking of the bond and the leaving group happening at the same time. And that's why it's called concerted, because these happen in concert. Watch. The nucleophile comes in, boom, hits that carbon, and at the same time, the nucleophile, or the leaving group leaves, okay? Nucleophilic attack and loss of a leaving group at the same time. They happen in concert, and that's why we call it concerted, all right? Happens at the same time. Now, a stepwise mechanism is where the leaving group leaves first. That arrow really should be like that. The leaving group leaves first, and then the nucleophile comes into the carbocation. It's a horrible arrow. This nucleophile comes into the carbocation. This happens step 1, step 2, and this is an intermediate, actually. It's not a transition state. It's an isolatable intermediate. Of course, depends on what the actual R groups are. But, all right, so this is a stepwise mechanism. It's not what we're talking about in this conversation, but I want you to see it. It looks a lot like the concerted, but it happens in 2 steps. All right, so let's talk more about the concerted mechanism. So first of all, if we think about this like in terms of cause and effect, we have the first cause would be the nucleophile comes in, but at the same time, while the nucleophile is coming in, the leaving group is leaving, right? Now, we call this SN2. S stands for substitution. N stands for nucleophilic. Nucleophilic, right? Nucleophilic substitution. And 2, what does the 2 stand for? The 2 stands for 2 compounds that are in the reaction. 2 compounds in the reaction. That's what that stands for. All right, so let's talk about how it happens now. The nucleophile comes in from the backside, and sometimes this is going to be a big deal, right? If we're trying to predict what the products are, then we're going to need to know where the nucleophile comes in. So if we have a nucleophile here, it doesn't want to come in here, right? Because there's a node here in this molecular orbital, and it can't come in there. But it can come in from the backside, and that's where it does come in. All right, so can you see the carbon here? And there's the leaving group. So the leaving group's leaving, and this nucleophile is coming in. So the nucleophile, its highest occupied molecular orbital, attacks the lowest unoccupied molecular orbital of the electrophile. So here's the lowest unoccupied molecular orbital. These electrons, they see that molecular orbital, and they say, hey, we can be in better shape if we go over there, and that's what they do. So all right, less sterically hindered electrophiles react more readily, and we'll show why in the next couple slides. But it turns out a tertiary, right, here's a carbon with 3 carbon-carbon bonds. So this is a tertiary alkyl halide. These do not react in SN2. In SN2, they do not react. Secondaries can react via SN2. Primaries are faster, and faster yet are methyl groups, right? So if you have a nucleophile, and it can go here, here, or here. If it has a choice of all 3, which is going to be the fastest, this one's going to be the fastest, right? So to consider this, let's look at the reaction coordinate diagram. Well, this is sort of a restatement of what we said just there, but let's move on to the reaction coordinate diagram. The reaction coordinate diagram is here, and you've seen this before. So the transition state, recall, is a mix, right, of that and that, right? Here's the reactants and here's the products. So while this bond is forming, This one is unforming, and that's what we have here. There's the forming bond, and there's the unforming bond. Okay? So why is it that methyl halides react the fastest? Well, look at what we have here. We have a partial negative here and a partial negative here, right? And then we've got these electron groups here, right? Now, if they're hydrogens, they're pretty small. But if one of these is a methyl group, well, that's actually much bigger, right? The methyl group is much bigger. And if it's ethyl or propyl or whatever, it's bigger yet. So obviously, the more electrons that we have around here, they're going to be having a problem with this partial negative charge there, right? So that's what makes this slower, is that increases the energy of the activation state. So the activation state, if there's big electron groups, is going to be higher, and the higher the activation energy, the slower the reaction. So let's look at these three individually. If we have a methyl, right, we have a relatively low activation energy. If we have a bunch of electrons around that, well, those are going to be interacting with the negatives, the partial negatives of the nucleophile and the leaving group there, right, in the transition state. So it's going to be higher. And then if we've got 2 electron groups, it's higher yet. And if we have 3, it just doesn't happen, right? So 3 electron groups around there, we're not going to get a SN2 reaction. All right, and that's it for SN2 reactions for now. We're going to be practicing these things a lot. All right, good luck.